Hello everyone, I'm Nicolas Isoart. In this video, I will introduce a linear time algorithm for the k-cutset constraint. This work is done with Jean-Charles Regin at the I3S, a French lab of the Université Côte d'Azur. So, the outline. Since the k-cutset constraint is for the TSP, first we will introduce the traveling salesman problem. Then we will show you some TSP solving methods, like relaxations and how the TSP is modeled in CP. Then I will introduce the k-cutset constraint and how we perform the consistency check and its pruning. Finally, I will show you some experiments and I conclude. The TSP is a problem that is easy to state but hard to solve. It has for data a list of cities and the distance between each pair of cities. It is constrained by two constraints. First, visit each city only once. Then find the shortest cycle. The combination of these two constraints makes the problem NP-hard or NP-complete depending on the variance. On this slide, I display two graphs. On the left, a node set, and on the right, a solution for the traveling salesman problem represented by blue edges. When the problem is NP-hard or NP-complete, a solution is to relax some hard constraints. As I said, the TSP is modeled by two constraints, the connectivity, it's that each node can be reachable from each other node of the graph, and each node must belong to a cycle. If we relax the connectivity, we obtain the minimum cost assignment problem that is solved in polynomial time by Hungarian algorithm or by flow algorithm. If we relax the fact that each node must belong to a cycle, we obtain a minimum spanning tree that is solved in polynomial time by Kruskal or Poem. An MST can be improved to a one tree, that is, an MST plus an one minimum weight edge that introduces the idea of a cycle, but not every edge belongs to a cycle. This is exactly the idea of L-Denker-Lagrangian relaxation, who starts from this lower bound and to try to make a convergence towards the optimal solution. Unfortunately, in practice, the Lagrangian relaxation can be very slow. So, in constraint programming, when we use a Lagrangian relaxation, we use some filtering deduction in order to speed up the computation. For the TSP, let's make the hypothesis that we know a non-optimal tour having a length equal to k. Then we can try to add edges in the lower bound in order to detect if an edge is mandatory for the existence of a Hamiltonian cycle of a cost lower or equal to k, or if the edges can belong or not to the solution. So, making deduction allows us to greatly reduce the number of edges in a graph. For instance, the left graph is a complete graph with 100 nodes. After a propagation round, 86% of edges are removed, so it greatly reduces the search space and therefore it reduces the computation times. In addition to cost-based constraints, 2 years ago in CP, we introduced the k-cutset constraint. We need three definitions. The first one is the definition of a cut. A cut is a partition of the graph node in two disjoint subsets. Then, a cut set is the set of edges having exactly one endpoint in each partition of the cut. Finally, a k-cutset is a cut set containing k edges. So, in this graph, I represented two k-cutsets. The first one, k1, is a two cut set because it crosses two edges. The second one, k2, crosses four edges, so it's a four cut set. The first remark we made in the proposition 1 is that any Hamiltonian cycle contains an even and strictly positive number of edges from any k-cut set. Otherwise, if we have one edges in a k-cut set, then there is a bridge in the graph, so there is no TSP, there is no Hamiltonian cycle. If the graph is disconnected, then we cannot find a unique cycle connecting all the nodes. In CP, we have variables, we have domains. So the TSP is modeled with a graph variable, G, containing a node, X, and two sets of edges, M, that is the set of mandatory edges that are identified by filtering algorithm or the branch and bound that branching on the edges, and O, the set of optional edges. The purpose is then find mandatory edges, and to remove optional edges. In the graph, we presented the blue edges as the mandatory edges and the dark edges as the optional edges. The removed edges are just removed from the graph. So for each k-cutset, the k-cutset constraint ensures that M1 plus O1, the set of mandatory and optional edges belonging to this cutset, is greater or equal to 2, otherwise the graph is disconnected or there is a bridge, and it ensures that there is no cutset containing k mandatory edges such that k is odd. Indeed, M must be even if there is no optional edges, otherwise at each time we leave a component, we must return the component, so that is an even number of edges. Then, there are two cases of inconsistency. The first one is the one where the graph is disconnected or there is a bridge. So, there is a k-cutset with M1 and O1 with a cardinality lower than 2. So, there is Target algorithm in order to find if there is a bridge or if the graph is disconnected. Since we will need to find the two cutsets, we will use the Int'l algorithm. We found the connected components, the bridge, and the two cutsets in only linear time. The second case is the one we will focus on. That is the case with k mandatory edges such that k is odd. So that is a failing k-cutset because there is no TSP if such a k-cutset exists. However, such a k-cutset can be hard to find since checking all the k-cutsets in the graph is exponential since there is an exponential number of cuts in a graph. So we will see how checking a linear number of cutsets is enough to ensure that the consistency is checked. Here there is an example where M plus O is lower to 2, so there is a bridge between two components of the graph. The second case is where M is odd and O is equal to 0. So we have a 5 cut set with 5 blue edges, so 5 mandatory edges. Starting from left, there is no TSP since we go right, we go left, we go right, we go left, we go right, and we are stuck. So there is no TSP in this case. So how to find this cut set? So first, we compute the connected component in the graph in which we remove the mandatory edges. So we have connected component of optional edges only. So that is linear to perform such an operation. Then for each connected component, let's see, we check if the number of mandatory edges outgoing of this component, that is the edges having exactly one endpoint in this component, is even. If this property holds, then it cannot exist a k-cutset with k mandatory edges such that k is odd. I explain. Let's have two connected components of optional edges such that the two connected components have exactly an even number of mandatory edges outgoing. So the two cutsets induced by one component and the other are valid. If we merge the two connected components, then we will have the mandatory outgoing edges of the first component plus the mandatory edges outgoing on the second component. So an even number plus an even number is an even number, minus the edges that have one endpoint in the first component, one endpoint in the second component. But the edges is count twice since it is first count in the first component, it is second count in the second component, so we have to subtract this number twice. So each merge of the connecting components will create an even number of edges in the cut set. By this operation, we can construct every cut set of the graph, so an exponential number of cut set. But if each connected component have an even number of mandatory edges outgoing, then we cannot construct a k-cutset with k mandatory edges such that k is odd. So if the point 2 is valid, then there is no k-cutset such that k is odd with k mandatory edges. Checking each connected component is in order n, so the overall time complexity is linear. We have two examples where we merge the connected component in C0, C1, C2, C2, C4. That is consistent since we can see that each node have an even number of outgoing mandatory edges. Therefore, no cut set with k mandatory edges such as k is odd can be constructed. In the right graph, however, we see that C5 and C9 have 3 outgoing mandatory edges, so we can construct, for instance, the k-cutset with C8, C9, and for the other part of the cut, C5, C6, C7, that is a 3-cutset with 3 mandatory edges. So that is the key to lowering the number of considered cutsets in the graph. We note that the first algorithm we published in CP19 was an algorithm checking with k equal to 3, and this algorithm was quadratic. For the pruning, there are 3 cases. The first one, as I previously said, is Int'l with thin algorithm is the case of a 2-cut set, m plus o equal 2. So we have to deal with point 2, that is m equal to k minus 1 is odd and o equal 1. In the case where m equal to k minus 1 is even and o equal 1. So we say that the point 2 and the point 3 represent the prunable cut set. Here is an example. So the point 1 is a 2-cut set, so with 2 edges. Point 2, we have 3 mandatory edges for a k-cut set. So k minus 1 equal to 3, k equal 4. So the fourth edge must become mandatory in order to have an even k-cut set. In the point 3, we have a 3-cut set with 2 mandatory edges, so the non-mandatory edges must be removed in order to not have a 3-cut set with 3 mandatory edges. So we'll mainly focus on the point 2 and 3 in the next slide. Now I will give you an example of an execution of our algorithm performing the pruning, and then I will give you a more formally sketch of the algorithm. So let's take this graph. The graph 1 is the starting point from the algorithm. This graph is a graph where we removed all the mandatory edges and we merged the 2 edge connecting component. So it remains only 2 edge connecting component connected by bridge, that is the black edges in the graph. Then we add the mandatory edges. Note that, for example, the node B and A are connected by one blue edges, that is a mandatory edges, but it can be a path. So the path is merged in order to have one edges connecting B from A. We note that each node has exactly one parent that is an optional edge except for the root. Then, for each leaf of this graph, so that is B, F, G, H, E, and G, we know that there is no child, so there is only one optional edge, that is the parent of the node, that is optional. That is a key to our algorithm. We have to start from the leaf before treating the parents. The post order allows us to do that. Here the post order is B, F, G, D, H, E, G, E, C, A. So let's run the example. Starting from B, we can see that B has 3 mandatory outgoing edges and 1 optional outgoing edge that is connecting to A. So if we want an even cut set, we have to make mandatory the edge BA. So we do so. Then we continue. For F, we have 2 mandatory outgoing edges and 1 optional outgoing edge that is connecting to D. If we want an even cut set, we have to remove FD. So we continue with G. We have to make mandatory the edge GD. Then D has no more child, so we can make mandatory DC in order to have a 2-cut set around D. Then we have HE that is connecting to HG, so we have to make mandatory HE in order to have a 2-cut set. Graph 6, we have the node E. The node E, in order to have a pair cut set, we have to make mandatory EE. Then the node G, we have to make mandatory the edge GE in order to have a 2-cut set around G. Then in graph 8, the node E, having one optional parent with 3 child that are mandatory. So we have to make mandatory the edge EC. So in graph 9, C has 4 mandatory edges and 1 optional edge connecting to A. So we have to remove AC in order to have a 4-cut set. And when we are at the root, the execution of the algorithm is finished. In this slide, I will give you a sketch of the algorithm. There are 4 steps. The first one is to find the bridges with the DFS-based tangents algorithm. While searching for the bridges, we have to mark the two edges connecting component in post order. More precisely, the order of the component is set when it is backtracked in the DFS. Then we parse all the mandatory edges. For each edge, e.g., we increase the number of outgoing mandatory edges of both the two edge connected component containing E and the one containing G. Then finally, we iterate over the two edge connected component CE with the defined post order, and we prune on the neighborhood of the two edge connected component with the bridge that we previously defined. Note that the complexity is linear since point 1 is find bridges, point 2 is parse the two edge connecting component, that is at most n. Then we have to parse the mandatory edges. There is at most n mandatory edges in the graph. We then have to iterate again over the two edge connecting component, that is n component. Finally, that is a linear time complexity algorithm. Then some experiments. We selected a subset of instances of the TSPlib, a library of reference graph for the TSP, and we compare with the state of the art, that is the weighted circuit constraint with the k-cutset constraint that we introduced in CP19 with the weighted circuit constraint with the algorithm we presented today for the k-cutset constraint. We give for each instances the time in seconds, the number of backtrack, and a third column is there to give the ratio between the state of the art and the algorithm we presented. In addition, to the bottom, we give the mean solving time, the mean backtrack, and the mean ratio. So we observe that our algorithm allows us to gain an improvement factor of 30% of the solving time and 10% in backtracks. It suggests that almost all the k-cutset we found are in fact 3-cutset. We recall that the state-of-the-art algorithm deals with 3-cutset, the quadratic algorithm. Therefore, the improvement of the complexity of our algorithm allows to greatly improve the solving times compared to the number of backtracks. Note that some instances, such as PCB442, is solved faster with less pruning and a quadratic algorithm than with our algorithm. It is due to the Lagrange generalization that disrupts the filtering algorithm by losing the monotonicity of the filterings. Nevertheless, we gain 30% of the solving time with the linear time algorithm that is much simpler than the previous algorithm. Note that even if we improve the complexity of the k-cutset constraint, this constraint is not the only one of the model. Therefore, we cannot expect to reduce the solving times as much as the complexity has been reduced. Next, we compare the different k-cutset size we found while solving some instances. So we give the mean k-cutset size and the max k-cutset size. As we can see, the mean k-cutset size is equal to 3, so the previous algorithm found almost all the k-cutset or finally found them, and the max k-cutset size is 14.5. To conclude, we introduced a linear time algorithm checking the k-cutset for any k. So the state-of-the-art algorithm, we recall, deals only with k equal to 3, and it is a quadratic algorithm. So our algorithm improves both the complexity and the k-cutset it checked. So it leads to an immediate improvement of the solving times. Most of the k-cutset are in fact of size 3, so it explains why the quadratic algorithm finding the 3-cutset improve so much the solving times. For the perspectives, we show that with the k-cutset constraint that it leads to a huge reduction of the search space and it greatly improves the solving time. So a good perspective will be to integrate other structural constraints, and when we want to scale to larger graphs, algorithm dealing with all the edges of the graph can be quite heavy, so develop incremental algorithm could be a good idea in order to improve the efficiency of the codes. So that's it. Thanks for listening.